Hey everyone, welcome to today's webinar, which is being sponsored by Megger Baker Instruments. Thanks to the sponsorship, access to the live presentation and recording are available to ESA members for free. As a leader in installation test technologies, Megger Baker has developed the most innovative equipment available for motor testing. Megger's focus is to combine the latest advanced technology with an extensive depth of experience. This results in dependable yet comprehensive predictive maintenance and motor reconditioning tools for customers. Megger Baker continuously drives itself to solidify its customers' competitive edge with sophisticated and reliable test solutions. These comprehensive instruments compile information via online and offline testing. The online test equipment searches for power, torque, overcurrents, load, efficiency, and many other problems within the running motor. This monitor can be connected via a safe connection at the motor control center, quickly determining problems that are apparent within the motor process. The offline equipment tests for faults within the windings, coils, or leads. These testers simulate the spikes associated with startup, finding problems that are above operating voltage. This allows time to repair or replace equipment on your schedule rather than the machinery's. Helping customers stop motor failure is Megger Baker's goal. Thanks again to Megger Baker for its support of this webinar. And here with our presentation is Matthew Conville.
Thank you, Matt, and thank you, Megger Baker, for your sponsorship of this webinar today. Today, we're going to talk about low voltage variable frequency drives and the accessories we want to use for proper operation and power quality. Again, my name is Matthew Conville, and I'm one of the ESA staff. I'm a technical support specialist. If you guys have any questions today and you're using the web browser with the Zoom plugin, you can use the chat function. You can raise your hand by clicking the button, raise your hand, wait to be called on, and then ask the question verbally, or you can submit your written question in the Q&A, and we will get to that. If you've just joined using the web browser, again, you're going to want to click the raise your hand. Then you're going to want to confirm your audio source to ensure that you've joined correctly, and then you can ask your question verbally. With that, let's go ahead and get started. So what do we want to accomplish today? Well, by the end of our webinar, we hope that you guys will be able to determine what drive accessories might be required in an application. And then we're also going to know what type of power quality devices can we use to improve the motor-driven system reliability and potentially reduce harmonics. And then lastly, we want to have a basic knowledge of some of the impacts on AC machines when we're using a variable frequency drive and we're operating at variable speeds. So a lot of times I get asked the question, why do we want to accessorize? Whenever I buy the drive, doesn't that just give me everything that I need? And the answer is yes and no. In the most basic of applications, there may be no need to actually accessorize. But as we want to improve reliability and we want to control things more precisely, then the answer is yes. So in some instances, we want better control of the application. We need more precise control of speed and position. So we have accessories for that. We may want to monitor the motor's health or the performance of the machine. So we have some accessories that we can use for that. We could want to integrate the drive into the control system. Maybe we don't want it to be standalone. We want to be able to control it remotely, or we want to know what its functionality is, what it's doing at an exact moment in time. So there's different accessories for that. And lastly, we might actually want to be able to troubleshoot from the control panel or the drive panel more easily. And there's different things that we can do to accomplish that as well. So some of the most simple ones are going to be speed control accessories. There's two basic ones that we most commonly see for speed control, and that's going to be an incremental encoder and a resolver. So here's an example of a Nidec Avtron light mill duty incremental encoder. And here's an example of a Dynapar heavy duty R56 resolver. And what these do is they actually tell us the rotor's position along with the rotor's speed in any instance in time. It's going to give us what we call closed loop feedback. What that means is the drive system almost always creates a motor model in most of the control methods. And there's a webinar that I did on that earlier this year. When we use these closed loop feedback devices, they're actually confirming to us where the rotor is, so that the drive system now has precise control of the ID and IQ current, so that we can develop the torque and speed that we want. One of the things that I had to learn the hard way is that incremental encoders and resolvers do not use the same IO card or power supply. So if we want to change from one to the other, we need to make sure that we have the appropriate power sources and cards for that. So when I talked a little bit about speed control, here's an example of a speed profile or a preset that we might want. So in this operation or process, we may want to accelerate, maintain a certain speed, and then decelerate over time. When we don't use an encoder or a resolver, it's very possible that our speed profile might look like this, where here's our preset and here's what we actually have. We've got large deviations to get to the appropriate speed over time. And then as we get to our speed set point, we'll actually overshoot or overspeed. And then the drive will recognize that it's actually over its set point, and then it's going to undershoot. By the time, in this instance, by the time that we've actually gotten to the appropriate speed that was called for, we're almost 50% of the way through this cycle. This could actually lead to issues with process and product quality for our end users. So that's a good reason for us to use speed control accessories such as encoders and resolvers. And as you can see, when we have appropriate speed control, this dashed line here, we very closely follow our set point. So we'll have better process control. So let's dig a little bit more into incremental encoders and resolvers. So incremental encoders typically have a DC power supply. And this power supply is usually somewhere between 5 to 15 to 24 volts DC. And then the output waveform that the incremental encoder produces is a square wave. And those signals are usually called A and A naught, B and B naught, and a Z marker. And the Z marker will tell you a revolution. Now these square waves come in pulses, as you see here. So you're looking at these different pulses, and the encoder actually gives you so many pulses per revolution, or PPR. Most commonly, we're going to see 1,024 of these pulses per revolution. A lot of encoders come with a 1024 PPR. The closer we're going to be towards zero speed, and we need to maintain zero speed or torque at near zero speed, a 1024 PPR encoder might actually not be enough. We may need one that pulses 2,048 times or 4,096 times per revolution, so that we have a better understanding of the position of the rotor near zero speed. One of the things that's a common concern when we use an encoder is that we might get some transients or some harmonics here on this line, on our waveform that is being viewed by the IO card. And that's usually the result of using either improper cable or cable that was not properly terminated. So it's always best to work with the encoder manufacturer to use their recommended cable, and then work with the cable manufacturer to use the appropriate grounding methods or EMI clamping methods. Most commonly, we're going to see incremental encoders being used in AC induction, AC synchronous, AC synchronous reluctance, wound rotor motors, and in DC machines. The second type of speed control is actually called a resolver. And resolvers, they're a little bit different. So we said in DC, they have, or in incremental, they have a DC power supply. Resolvers have a very specific AC power supply that they use. And the output waveform looks like a cosine and a sine wave. So it has a sine wave and a cosine wave. And what it's going to do is it's going to provide a very precise voltage at the known position in each revolution. And that's what the I/O card is looking for. So it has to be an analog card so that it can sense that voltage. Most commonly, we're going to see these used in AC and DC servo applications, and also in some positioning applications where we're wanting to do turn counts. So you might see some resolvers that are talked about as being like a 50 or 100 turn resolver, which means it allows it to make 100 revolutions or 50 revolutions. One of the newer types of encoders, and one that I really like, is called an absolute encoder. An absolute encoder is used for positioning, and you can actually use it for speed control as well. Its output waveform is different. It's a digital telegram. It's made up of ones and zeros. It could be in binary or hexadecimal or some other form. And it's constantly communicating its position. So instead of waiting for a pulse for a change like we are with a resolver or for an incremental encoder, this is constantly telling the drive system what position it's at. What's really neat about these is when the absolute encoder is power cycled, it actually remembers its location. So it will tell the position that it was last in. The only caveat to that is if we lose power to the absolute encoder and the shaft is spun, we might actually not have the same, we might not be in the position that was last remembered by the absolute encoder. It's very commonly used in applications where we need to move a extremely precise distance, or we're wanting very precise speed control where it needs to constantly communicate. These encoders, again, much like the resolvers and the incremental encoders, we want to follow the manufacturer's recommendation for cabling, and then the encoder, and then the cabling manufacturer's recommended practices for grounding, so that we don't have any noise. When we want to monitor the health of the machine, we really want to look at a few different things. And we're not going to discuss all of these today in effort of time, but we'll talk about some of the different things for you guys to think about. We can do ground fault monitoring, temperature monitoring. We can have operator panels on the drive panel that will help us understand what's going on. We can use some of these IIoT devices. A lot of these are able to integrate into the drive system as well. You can do speed feedback, which we already talked about. And we can even do other condition monitoring devices, such as airflow, and in some instances, even vibration, just to name a few. When we think about variable frequency drives, one of the most common things that we see are ground faults. So a lot of drive systems now have ground fault monitoring. It's a parameter that has to be enabled. So a lot of times it's not turned on, or if it is turned on, it's at a default value that we may or may not want. It's usually set up in terms of percentage of rated amps of the machine, or in terms of percentage of rated amps of the power section. So it's really important that whenever we're setting it up, we take a look at it. We can set our own alarm and trip points as a result of that percentage rating. We can also display these values on the drive operator panel. You can display it on a HMI or human machine interface, or by any other means in the control system. If we've set it correctly, we can actually prevent catastrophic winding failure, which is pretty neat. The caveat here, so one of the things we have to be careful about is if we set our ground fault monitoring so low, if we have some sort of a transient event, we might get nuisance trips. So what I used to do is I would set what I would think to be a conservative value for a trip on the ground fault, and then I would set an alarm at what I thought would be something good for that application. And we would check to see how many different alarms we got over time. If that alarm seemed to be set appropriately, then we would just set the trip point somewhere between 10 and 20% higher than that. Temperature can be monitored by variable frequency drives. We have several different ways that we can do that. The drive itself, some of them are smart enough to where it can create its own winding temperature from the motor model and the amount of current that's actually being given to the machine. The downfall to this method is that it assumes a temperature rise that you have to input, and it assumes that it's constantly getting the appropriate airflow or velocity, and the temperature of the cooling air is sufficient. So if we have a shaft mounted or integral fan, like a totally enclosed fan cooled machine, and we're lowering our speed, the actual winding temperature is going to be different than what the drive is estimating. So what we can do to account for that is we can use temperature detectors, and they can be added to the drive via expansion boards, and then we can monitor our winding and bearing temperatures. We can set a custom alarm and trip temperatures for an application. What I mean by that is, let's say, for instance, we have a bearing, and the bearing is good for, 80 degrees centigrade for an alarm and 100 degrees C for a trip, which would be about 212 degrees Fahrenheit for a trip. And we're constantly operating somewhere in the ballpark of about 100 to 130 degrees Fahrenheit. So we may not want to set an alarm at 170 to 180 degrees Fahrenheit. We may want to set it lower, because over time we've seen that the bearing never gets that warm. If the bearing starts to get that warm, then we know that we have a problem. So instead of waiting until a failure may occur, we can use this for predictive purposes to see when something has changed. And that can actually help prevent bearing failures as well. The same can be said for windings. You might also add an ambient RTD, and this ambient RTD can be used in instances where we have wide ambient temperature swings, where it could go anywhere from 32 to 115 degrees Fahrenheit, or 0 to, let's say, 40-ish C over the course of a day. And you can just look at that change in temperature versus an absolute. And we can display all these things on the drive operator panel, again on the HMI, or even on somebody's computer if the industrial network is connected to somebody's computer or phone. Now, not all temperature detectors are actually created equal. So a lot of times we're going to see electric machines, and they're outfitted with switches, or colloquially like a click-on or a thermostat. And these are great for setting an alarm or setting a shutdown or to operate auxiliary equipment, but what they can't do is actually give you a temperature reading. Now, you could use a thermometer, and the thermometer might actually give you a temperature reading, but it's not going to give you any alarm or trip set points. So the things that we're going to want to look at using are going to be RTDs, thermocouples, and thermistors. If we're going to use a thermistor, we need to make sure that it's a negative temperature coefficient thermistor for temperature reading. The same thing is said for bearings. Now, one of the things that I saw for bearings a lot of times is that we thought we were doing a really good job of monitoring the bearing temperature by putting an RTD on the outer cap. Or in the instance of a white metal or a sleeve bearing, maybe we are monitoring the oil temperature. Well, that's great, and that does provide a relative term. In the instance of a white metal or sleeve bearing machine, if we have a large oil reservoir, we're not going to see a large change in temperature of the oil before the bearing gets hot. So it's always best, if we can, within reason, to actually get a RTD that you can sit either on the outer race of a roller element bearing or on the top of the bearing half on a white metal or sleeve bearing. The one thing we have to be careful about now that we're using a variable frequency drive, or even in some instances without a variable frequency drive, as soon as we put this RTD and it's coming in contact with the bearing, you have metal on metal contact. If this bearing or this housing or what have you, if the bearing is considered to be isolated, we've now created a ground path from the probe, the detector shaft that's usually made out of stainless steel, back to the frame or the end bracket. So now we're going to allow current to flow through the bearing, and we can create fluting as a result of that. So when we buy RTDs that we're going to sit onto a bearing, and we're going to use them in a variable frequency drive application or one where we have isolated bearings, we want to get an insulated tip for the RTD. So let's talk a little bit about operator panels. There's two basic types. You're going to have a basic operator panel and an advanced operator panel. Basic operator panels are going to give you very basic functions, just like their name calls. Start, stop, forward, reverse. You might be able to do some very basic monitoring. You really won't have a lot of access to the parameters of the drive. You can do very simple setups, but you're going to have very limited access for faults for troubleshooting. So you might actually have to carry the drive manual with you if you're trying to troubleshoot a drive fault. With advanced operator panels, now they're not all the same, but for the most part, they're going to give you all the same functionality as the basic operator panel. Also, they're going to give you access to almost all parameters, if not all parameters, and you're going to have advanced monitoring. So the temperature, your speed feedback, all the different things that we've added in, all those different accessories we've added in, you're going to be able to see those on the display. You can even make some tuning adjustments as needed as well. There's one thing we have to be careful about is, when we're making tuning adjustments, you might want to see what we call a trace function just to make sure that the drive and the motor are performing the way you want. But you can make changes, slight changes, from the advanced operator panel. The one thing that I found to be most beneficial is you're actually going to have much better access to the fault logs and the alarm logs. A lot of times it'll tell you what the fault condition is, and then what's in the troubleshooting guide of the drive system and the manual. A lot of times they'll put those exact things in there, so you have kind of a tree of decisions you can go through to see what caused the fault to occur. And then you'll also have some indicator lights as well that are going to give you status conditions. And that's going to be your run light, your fault light, and your alarm. And remember, a lot of our alarms are going to be things that we set in the parameter set, some coming from some of the accessories and some coming from just some of the basic parameter sets like ground fault monitoring in the drive system itself. Not every drive do we want to be standalone. So we need to have communication cards to be able to do that. Some drives come with communication cards and some have to be procured with it. And what this does is it gives the drive the ability to communicate with other drives on the same network, industrial network, with other PLCs on the network, and even with any other device that we may have, laptops, it could be tablets, smartphones, whatever has access to the industrial network. We have to be really careful because not all these communication cards are created equal. So here's an example of one from ABB, and it's an Ethernet. And Ethernet is very common. Here's an example of one from Toshiba, and it does Ethernet IP, but it also does Modbus. So I'm going to go through a couple examples here, or name some of the different communication methods. There really isn't anything that I want you to take away from this other than there's so many different ones that it's really important that we know from the end user what they want. Some of them are Ethernet IP, Field Bus, Modbus, Modbus RTU, Profibus, Profinet, and ProfiSafe. So as our drive systems have gotten more intelligent and our applications are getting more intelligent, we're really wanting to protect the people that are in those areas. And we have safety ratings associated with that. So these drives now are more intelligent than that as well. So they have what we call STO, or safe torque off functionality. They have safety e-stop functionality, and they even have safety from a communication perspective so that the communication card is safe, like what we see here with the ProfiSafe. One of the things that I found to be very helpful and not very expensive, but a really good time saver, was actually having data storage cards for the drive. So a lot of drives, especially the more advanced ones, will allow you to have a what they call a smart card or a compact flash card that you can store the drive's parameter set on. When these drives fail, or if we have a control unit, some drives has a control unit, if these control unit fail or they get power cycled, sometimes they lose their parameter sets. And when they lose their parameter sets, we can upload or the parameters from the smart card straight to the control unit, and you'll be up, back and running very quickly. So you might be looking at, let's say $75 to $200 or so for a smart card or compact flash card. But in the middle of the night, whenever somebody has to do a drive change out, that expense is very small in comparison to having to call a bunch of people in and going back to retune the drive. You can plug in the smart card, you can upload the parameter sets, everything can be the exact same as it was, assuming that the last file got uploaded to the smart card, and you're back up and running and going. Drives create power quality issues, or as IEEE calls them, disturbances. And they coin a disturbance as any change in the power, which is the voltage, current, or frequency that interferes with the normal operation of electrical equipment. So IEEE lists some of the following power quality problems that need to be taken a look at, and that's going to be over voltage or under voltage, sags, swells, transients, noise, harmonics, and grounding. So nowhere in here will you see the term spike used. They're very particular in their naming. They don't want it to be ambiguous. So for us, spikes are typically going to be in the form of grounding, harmonics, and transients, and sometimes noise. So it's really important that we delineate what these are. As I said, VFDs can actually contribute to many of these power quality issues. And not only is it going to have an impact on the downstream devices, like the electric machine, but it can also have an impact on any of the things on the line side as well. Well, what exactly do I mean by that? Well, so here's an example of some of these transient and harmonic events that we're talking about. So on the line side, we're going to get this notching that occurs in the current. And this is a 6-pulse drive here that does regeneration, or no regeneration, with a diode front end. And here's one that actually has a IGBT front end for regeneration. And you can see that it's created power quality issues on the line side. On the load side, we're going to have a bunch of little square waves that come together that are going to make our, what we would call a sinusoidal output. And as you can see, They vary in length. So since this is not continuous, again, this is some sort of a disturbance. Well, with our IGBTs and diodes, these front ends are going to create harmonics, just like I showed you. This can cause an impact, especially on very sensitive electronic equipment and other motors that are fed by the same source. If we have multiple drives fed by the same feeder, so we have like a main breaker, and then that goes into an MCC, and we have 10 or 15 drives, we can cause misfires of those drives because of all that notching that we've put on the line by not taking care of that harmonic content. Some utility companies actually enforce harmonic penalties. As drives become more and more commonplace, I really expect to see, this is just my opinion, that the utility companies are going to have a more strict approach to harmonic content, mostly because they're not going to want to put in the infrastructure themselves to account from that from their users. So what can we do to fix it on the line side? Well, if we have multiple drives on the same feeder, at a minimum, we need to use line reactors on the supply of each drive, unless the drive manufacturer says otherwise. There's only a few instances that I can think of where a line reactor wouldn't be of some benefit. An isolation transformer would be great, and it also helps limit the harmonic content quite a bit. The problem with that is they're big, right? And then you have losses associated with those, and then you have inrush associated with those. So it may not always be feasible, and they're expensive. It may not always be feasible to use an isolation transformer. If we do use an isolation transformer, we want to ensure that it has the appropriate K factor rating. The easiest way to remember it is if you're specifying a transformer for a drive, buy a drive isolation transformer. Some drives already have built-in filtering in their active front end, or they use other drive topologies with multiple pulses to actually reduce line side harmonics. If we're connected to a utility grid, directly to a utility grid, we either have to have an integrated or an external LCL, which is inductor, capacitor, and inductor filter, and that's required to mitigate harmonics. So here's just a couple examples of some inductors and an example of an LCL filter. On the load side, we're going to have IGBTs that are going to be gated on and off. And that's typically in a pulse width modulation, or PWM frequency. Effectively, we're going to have thousands of square waves that are used to create an output voltage and frequency. And you can kind of see that here. So here's all those little square waves to create our output. As our cable gets longer, we can get what we call a ringing up effect. And with this ringing up effect, we could have peak voltages that are 2 to 3 times the DC link voltage of the drive system. And this can cause turn-to-turn shorts in our windings due to a steep front phenomenon, or DVDT, and peak voltage. So the main thing that we got to be careful about is not only are we worried about that peak voltage, which is going to be somewhat like what you would expect to see with our surge testers, but also rate of rise, which is DVDT. So when we think about our surge testers, we always have a time base that we set it at as well. So here's an example. Here's one of 9 feet, and you can see the voltage, it increases a little bit as compared to what it's supposed to be. If we look at one that's 500 feet at the same carrier frequency, now we have close to 700 volts, but we're over 200% of that. We're at about 1500, 1450 to 1500. So we've got that ringing up effect. So what can we do on the load side to help prevent things? Well, we can use load reactors, and they can reduce the ringing some, but really only for a short distance. A lot of drives are compatible, and almost all control schemes can use load reactors. There's a lot of white papers that are out that will talk about the effectiveness of a load reactor, and they'll tell you that as we've started to learn more, we want to look a lot more closely at what we call DVDT filters as a minimum. And these DVDT filters, they actually reduce that rate of rise and the peak voltage, and some of them can even reduce common mode voltage, which is another way that we get bearing currents, up to a medium cable length. So, somewhere in the ballpark of 300 to 500 feet. Again, you would want to work specifically with the manufacturer of the DVDT filter to see what it is, and then understand what the reduction you get is over time, over cable length. So just because it can work up to 1,000 feet, it may not provide you with the reduction in DVDT and peak voltage that you need. So just something to think about. And the last thing is sinusoidal filters. Sinusoidal filters are very, very effective for reducing DVDT and peak voltages for very long cable lengths. The problem with them is they're not compatible to be used with all variable frequency drives. And typically we only see them being used in volts per hertz or scalar operation. So if we're going to look at using any type of filtering, the major takeaway here is we want to work with the drive manufacturer to make sure that we're using the right one, and also that we're specifying the right one to reduce the DVDT and the peak voltage to a value that will be helpful for our windings. Common mode voltage is an issue. So bearing fluting is definitely an issue, and common mode voltages create high frequency voltage in the motor shaft and the frame. So we're going to get fluting potentially as a result of that. You can use inductive chokes. They can also be used to reduce some DVDT as well and common mode voltage. There's several manufacturers that create those and they have different configurations for that. One of the easiest ones is actually VFD cable with proper EMC and EMI terminations. It's actually going to take that high frequency voltage that we'll see, and it's going to dissipate it straight to the frame before it ever gets a chance to go to the motor shaft. One of the things that we need to understand is that not all variable frequency drive cable is created equal. So we may not want to use that, you can't just go pick one and that's going to work in every application. You want to make sure that you pick the one that's appropriate for your application and for the horsepower of the machine. The cable manufacturers, they will work with you to determine what's best for your application. They might always try and go to something that's more on the high end. If you tell them that you're worried about price points, but you need to have proper protection, they will work with you on getting what's appropriate. So let's talk about some of the things that happen to AC machines as a result of operating on variable frequency drives. Well, first we're going to have a reduction in service factor. So if we have a machine that's got a NEMA type nameplate on it and it has a service factor, that's going to go away. Unless it says that it's listed with a service factor on a variable frequency drive, which we'll get into that more here in a minute. We are going to have an increased risk for winding failures. And why is that? Well, we are going to have harmonics and transients on the load side of the drive system going into the motor. We're going to be at an increased risk for shaft voltages, and we're going to go over that and a little bit more as well. And as we slow the machine down, if we're using an integral fan, we may have to use turn down ratios. So as our cooling as our speed goes down, our cooling goes down, and we'll talk about that here as well. So what does NEMA have to say? NEMA says that effectively, as soon as we put a motor on a variable frequency drive, its service factor rating is 1, even if it had a 1.1 or 1.15 service factor rating. NEMA, this comes from NEMA MG1 Part 31, Part 3.7. And it says that a motor that is covered by the Part 31 standard, which is for use on an inverter, shall have a service factor rating of 1. So any NEMA motor that's conforming, or any nameplate that conforms with NEMA and it's an inverter rated machine, won't have a service factor. All other parts of NEMA MG1, they refer to unusual service conditions that actually take the rating from a 1.15 to a 1 as well. So if we look at Part 20 as an example, it says that induction machines shall operate under normal running conditions at a rated load and a variation in voltage and frequency up to the following. C is where we're worried. A combination in variation in voltage and frequency that is 10%. So if we have a change that's 10%, it's the sum of the absolute values of the change in frequency and the change in voltage, provided the frequency variation does not exceed 5% of the rated frequency. So more or less, if we operate a variable frequency drive, lower, that's a 60 hertz machine, lower than 57 hertz, then we've automatically gotten rid of that service factor from a 1.15 to a 1.0 in any other condition, along with the fact that 31.3.7 says that anytime we're using a motor on a variable frequency drive, it has a service factor of 1. So let's talk about what happens with windings. I talked to you about the fact that windings can see 2 to 3 times the DC bus voltage of a variable, of the VFD. And this DC bus voltage is somewhere between 1.35 to 1.51 times the RMS AC input. And these peaks are going to be seen at the drive's carrier frequency, which is usually somewhere in the ballpark of about 2,000 to 8,000 kilohertz. So as an example, if we have a 480 volt AC input, we could have upwards somewhere between 620 to 720 volts for our DC bus. And if we're at 200% of that, we're at 1,440 volts. So as you can see, with a standard insulation system here that meets Part 31, if we have a 720 volt DC bus, we might be over the withstand voltage that can be seen if we don't have the appropriate output filtering. And it's also asking for us to be partial discharge free at 1,025 volts. And it wants us to have everything to be able to withstand this at on a time base, or a rise time of 0.1 microseconds. Now, IEC is a little bit different. So on the 6034 standard, it tells us in 18-41 that it's going to use a rise time of 0.3 microseconds. And when we're on a converter, or what we would call a drive system, they give 4 different stress categories that are standard, which is A, benign, B, moderate, C, severe, and D, extreme. They also have one for S, which is specific. So if we order a IEC machine and we say we just want it to be inverter rated, we could have a stress category of A, benign, and it would be relatively inexpensive material that's used in it, because we're assuming that the peak voltage is only going to be 110% of what the actual voltage is. And we're seeing that if we don't use any filtering, that it's going to be 2 to 3 times. So if we're 2 to 3 times, we really need to be in this C and D category. So the major takeaway here is that if we're going to specify an IEC machine, we need to make sure that we're using the appropriate stress category. And we can also see the need now for the use of output filtering or a drive topology that lowers the DVDT and the peak voltage over distance so that we actually don't damage the windings. There are two types of current that can pass through bearings. There's common mode currents, which are created by common mode voltages, and that's done by the variable frequency drive and switching. And the other one is going to be frame currents, or what we call PE current. The one that we've got to be really worried about is we might have shaft grounding to help mitigate the ground current, but now we might have some of this high frequency common mode current too. So we might have to go to isolating both bearings instead of just one, or whatever the case may be. But it exists. So if we use a properly terminated VFD cable, that outer shield, if it's terminated right, will actually take that high frequency current straight to the frame, and it no longer becomes an issue. When we think about shaft grounding, if we're using shaft grounding, what you see here is if we don't have an isolated coupling, we can actually allow current to flow through the driven equipment back to earth. So if we've isolated the bearings and we put our shaft grounding brush on this end, you're going to create two problems. One, if this is not isolated, you can actually still have current go through the driven equipment. And now that we have shaft grounding on this side, you're actually going to create a difference in potential from one side of the machine to the other. So we're going to get circulating currents and the shaft as well. So you're going to create a change here, and that which can also be an issue for the bearings. So there's several ways to fix that. Again, we can insulate the bearings or the housings, which a lot of us are very familiar with, and then we can use various types of shaft grounding as well. But again, we can really reduce a lot of this by properly terminated VFD cable and the appropriate output filters. So one of the last things that we want to talk about is actually the impacts of using a variable frequency drive and really slowing down the speed of the machine. When we look at the speed of a motor, if it has an integral fan, and as the motor slows down, the flow is going to be reduced at a linear rate. It may not be linear, it may be more than linear, but it's going to be at least at a linear rate. But the other thing that we have to consider is we still have pressure drop inside of the machine. So not only are we limiting flow, but we may not be able to overcome the pressure drop that's needed, which basically means we're not going to move enough air across the windings, or in some instances get enough air across the bearings to actually keep things cool. So whenever we started seeing issues with rotating equipment, the motor manufacturers started creating motors that were inverter specific that had what they call a turn down ratio. And the turn down ratio, if we want to know what we need, we're going to take a look at what is the lowest operating RPM that we're going to be at on a regular basis, where we need to do work. And then we're also going to take a look at what is the rated speed, the base speed of the machine. So if you take the base speed of the machine and you divide it by the lowest operating speed that you need to do work, whether it be variable or constant torque, that's going to give you a ratio. So in our 4-pole example, if we needed to operate at 100 RPM, down to 100 RPM, and the nameplate was 1780, we're going to have a ratio of 17.8 to 1. So at a minimum, we would want to use a motor that is 20 to 1. We want it to have a greater ratio than what we need. As you get closer towards zero speed, having to maintain zero speed, just like we talked about needing to increase the PPR, the pulses per revolution on an encoder, we're going to want to increase the turn down ratio somewhere between 1,000 to 2,000 times. And these are just some common turn down ratios. You might actually see some motor manufacturers that give a 20-to-1 variable torque and a 10-to-1 constant torque, or they may both be the same. But the moral of the story is we really want to just pay attention to what turn down ratio is required for the application. So let's kind of recap things, and then we're going to open it up for questions. We learned today that encoders are great accessories that are going to give us better speed and position control. Operator panels, whether they be basic or advanced, are going to be great for motor-driven systems for troubleshooting and programming. If we use an RTD or a thermocouple or even a thermistor, we can provide real-time temperature feedback, and we can promote predictive trends so that we can actually prevent or understand whenever we have a step change that might cause a failure in the future. Variable frequency drives, depending on their topology, may require line side filtering for proper operation and reduction of harmonic content, especially if we have multiple drives on the same line. Motors just perform better with load side filtering. And the reason for that is it's closer to a sine wave. We're reducing that rate of rise and we're reducing those peaks. Proper VFD cables with terminations can actually reduce high frequency common mode voltage. And that's a second way that we can cause bearing damage or fluting. And lastly, if we're going to reduce the speed of the machine, again, we're already in violation of what we would consider for a service factor. We really need to take a look at, should we be using a turn down ratio since we're going to be operating in variable speed, so that even though we may not have a winding failure, maybe we're not going to be able to provide enough cooling air to actually cool the bearings appropriately. As a reminder, if you guys have questions today, you can use the chat, raise hand function, or the Q&A, and we'll be glad to answer them. Tomorrow, you're going to be emailed a link with a survey if you'd like to provide feedback. We always appreciate your feedback on how we can improve or what you liked. Tomorrow, you're going to receive a link for a Google Classroom quiz over today's webinar. And here in the very near future, this recording is going to be available for view for free. Thank you to our sponsor, Megger Baker, at esa.com/training/webinar recordings. And all the other ones from this year are there as well if you haven't taken advantage of those. And next month, we're going to have a webinar for DC voltage redesign by the one and only Chuck Young on August the 18th from 12 to 1 Central Standard Time.
So if anyone has any questions, go ahead and click that raise hand and we can open up your mic, or you can type in your question in that Q&A panel.
And you can also use the chat function as well if you'd like.
Well, Matthew, I'm not seeing any questions.
I'm not either. If you guys do think of some, feel free to email technicalsupport@esa.com. Or you can email me directly at mconville@esa.com. And we've gotten a few chats that said that they didn't have any questions at this time. So thank you guys for joining us today, and we can't wait to see you next month for our DC voltage redesign with Chuck Young.